Hello, this is a video on conditional probability. What is conditional probability, first of all? It is, let's see, conditional probability. It's the probability that an event B will occur given that another event, like A, has already occurred. So let's write that out. So the probability that event B will occur given given that another event A has already occurred. So the two events are dependent. Okay, so that's the idea of conditional probability. So we've already looked at the and the or and some of the other things. Let's look at a contingency table, or it's a two-way frequency table that has data from two categories. So you do have a couple problems that give you data in this kind of setting, and this is a conditional probability. And let's see how we use this table. Again, the table is just a contingency table. But let's see how we use this type of table to find our probabilities. So, I don't know why I'm such a perfectionist on this kind of stuff, but I am. I always have my ruler out. All right, so let's do that, and then 1, 2, 3. 1, 2, 3. All right, so here's my little table I drew, and we're going to have males, we're going to have females, and we're going to have a 2-year, and I just stole this from the book, but this is a 2-year, this is a 4-year college or school, and this is a graduate. So graduate school is beyond your bachelor, so beyond school. Beyond your first 4 years of college, you go to graduate school. So let's say we have 1866, 4,324, 149, 2462, 5517, and 1954. So here is an example of this table, and let's do a couple conditional probabilities for this. First of all, the word sample space kind of comes up. Sample space is like how many possible outcomes do you have? So we always have our sample space as like our denominator on our probabilities. So it's like how many things you have. So if you're rolling a dice, you have 6 options, right? For 1 through 6 on a dice, so you have 6 as your sample space. For this one, for our sample space, for every single thing, there is, if we add them all up, we have a total sample space of 17,472. So we added up all the numbers to get that. And let's look at a couple of problems we might see. We'll see the probability of being a female. That's it. Just a female in general. So this is a conditional probability. They have to be in the school, and now they're going to be female. So what you do is we're doing the total, right? Just females in general. So we add up all those different females in the different categories. So 2462 plus 5517 plus 1954. And we're doing it over the whole thing. So the whole sample space is the 17,472. We add these ones up, which is going to equal 9,933. And then we divide, and we're going to get about, do a wavy for about 0.59, or you could say that as 59%. So there's 59% of females represented from this chart in the colleges, 2, 4, and graduate school overall. So there's more females than males. So you can tell some information from that. Higher probability of a female. What if you want the probability of a female grad school, and just a straight line. So what are we saying? We're saying, okay, what is the probability that they are a graduate student and female, or not and, if they were female. So you have to, that's what the line kind of means. What if you were this one, if this one also? And that's kind of the idea of that conditional probability. And that's what that line symbol means is, well, what about, it's like the probability of this one given you were this one. And that's how you kind of think of that line. So look at our chart. Graduate school and female is 1954. But I'm not asking of the total number here. What I'm asking for, what's my sample space, is graduate school. Okay, so that's just these two numbers here added together. So that's 1349 plus the 1954. And that's going to give us about, oh, same thing. Oh, wait, this one was 57. I wrote 59. 0.59. I was reading my notes wrong, and I wrote that one as 59 when that was a 7. Let me just divide it myself. 9933 divided by 17,472. Yeah, 0.57. This one should have been a 7. I just read it wrong. Sorry. You're probably, if you did it on your own, you're like, wait, she got 59 and 59 again? This was 57. This one is 59. Still really close to the same number. And again, you could say that as 59%. Either way. All right, so let's look at another one similar. What if I say the probability of a 4-year male? What am I asking? If you're male, what's the probability you're in the 4-year, right? So here we are as 4324 as the people that are both 4-year and male. So 4324. But what is going to be my denominator? So here we use the second one, grad school. So here we're going to use the second one as well, all males. So we did the ones that were 4-year and male here. And then on the bottom, we're going to do the 4324 plus 1866 plus 1349, all 3 years of males. So numerator, denominators, all of those. And this is kind of, whoop, there we go. That's kind of smushing them together. So if I divide these, it's 0.57, another one. And that really is 57. So these are 57% or 0.57. All right. Lots of 57s, 59s. That's not on, they're not always going to be close to the same. It's just the random ones I picked. Okay, so second one went with denominator. Togetherness was our top there. All right, that's kind of how you'll see these type of problems in a chart. Let's look at them in a tree diagram and kind of look at a general formula you could use. So I've taught 15 years, and I finally saw a book that kind of drew the tree diagram in a way better way than I've always done it. Yeah, they did a branches like this, like you draw the line all the way out, and then there's a branch. In and out. I don't know. It was a lot better than I'd ever thought of. So let's go with people who graduated from high school and people who didn't graduate. And let's go with people who are happy as the second branch, and not happy, and happy, and not happy. All right, now let's put probabilities with these. Let's say the probability of being a grad from high school is 85%, and 15% of people did not graduate high school. And let's say that 90% of the people who graduated high school are currently happy, with 10% of those people being not so happy. And people who didn't graduate, 60% are happy, and 40% are not happy. So here is our table given a tree diagram. One thing I kind of want to show you is the probability of B A, event A given B, right? So this would be the probability of A and B divided by the probability of A. And that's all of A, not A and B, and I'll explain what I mean by that. So let's look at some examples. So this is our general idea or formula that they kind of give us when we are given percent. So either from a word problem and you're given percents, or you're given a tree diagram. It's a little different than the chart, because the chart you're adding the different numbers, whereas this one you're given the probability percents. So let's look at a first one here. What is the probability of being a graduate and happy? This is an and happy. How would we just do that one? It's kind of like the top, right? It's not a line one or a conditional, but what is the probability of this one and this one? Well, graduate is 85% and happy is 90. What did we do with and? We timesed our probabilities. So we'll take this one times this one, which is going to give me about 0.765. So about 76 or 0.765 percent of people are graduates and happy. So 75% or 77-ish percent. What if we said, question 1, 2 with the trees. What if we said, okay, so what about graduate happy? Totally different problem. What if it's saying, okay, what's the probability of being happy given you graduated? That's the question this is asking. So we have to use this idea. So we know the and, which is 0.765, and we need to divide it by the total probability of A. We don't have that right now. A happens to be our second one, which is happy. So what's the probability of completely being happy? Kind of like we went on this problem with the second one, right? Being our denominator, our graduate school, or our male. It's the same idea here as we have to go with happy. Happy and general are both these two lines. So I need to get this probability here because it will times these two together, and this would give me 0.09. So the probability of being happy is these two added. 0.765 plus 0.09, and that's how I'm going to get that denominator of completely happy. That threw me for a loop for a little bit when I first looked at these because I forgot the other line has a happy. I don't know. So let's see what we would get. So we're going to take 0.765, divide it by the 0.765 plus 0.09. Oops, I forgot to put in a number on my calculator. Okay, so here's what I put in, enter, and I get, oops, 0.765 plus, oh, did you see my error? I was like, I didn't get the same answer. Actually, oops. So 0.765 divided by 0.765 plus 0.09, not 0.06, is going to be 0.895. All right, or 89.5%. Okay, so that is kind of the idea of a conditional. So you have this formula you could use that might help you with some of the different problems that you're given, whether they're a tree or just a word problem. Or you can use our idea from the chart. All right, hopefully this video helped you do these problems.